And whenever you are ready, David, you can go ahead.
Okay, thank you. Hi everyone. First of all, I would like to thank the organizers for giving me the opportunity to be here today. This time I'm going to talk about membranes in AdS4 orientifold vacua and the weak gravity conjecture, reviewing the results of a work that Gonzalo Fernández, Fernando Marchesano, and I have recently finished as a follow-up of a previous collaboration with Joan Kiran. The main goal of this project is to see how well the weak gravity conjecture and the AdS instability conjecture hold up when we test it in systems that have membranes acting as domain walls between different vacua in AdS. So the structure of the talk will be as follows. I will first start introducing the topic and motivating why we think these kind of systems are interesting in the context of the Swampland program. I will describe the setup we are working with, and then review the properties of the 4D membranes that we put in this setup. First in the smeared approximation, and then going beyond the smearing, introducing back reaction in the geometry. This will all summarize the results that we already had with Joan Kiran. And next, we will put it into work in some more specific examples, especially working in factorizable toroidal orbifolds and getting some, we think, pretty general equations to evaluate whether the system satisfies or not the weak gravity conjecture. And we test it in several examples. Finally, I will wrap up with some conclusions. So let's begin. In order to distinguish between all the huge amount of effective field theories, the ones that are compatible with quantum gravity, a very interesting approach that has been taken by the community in the recent years is to propose different conjectures stating the expected properties that these quantum gravity theories should have. And I want to focus in two conjectures, the weak gravity one and the AdS instability conjecture. The weak gravity conjecture states that given a gauge theory weakly coupled to gravity, there always exists an electric charge state satisfying that the charge to mass ratio is greater than the charge to mass ratio of an extremal black hole. This has there are many reasons why we think this is true. For example, it provides a quantum gravity abstraction for recovering global symmetries when we go to small coupling. And also it provides a way for extremal black holes to decay. When we apply this conjecture to the case of the Ramon gauge fields and p-branes, what we obtain is this condition between the charge and the tension of d-branes. More recently, this conjecture has been refined by Oguri and Baffa. In this refinement, what they say is that the bound of these inequalities only saturated when we are working with BPS states in a supersymmetric background. So in line with this last refinement, a new conjecture was proposed, the AdS instability conjecture, that says that any non-SUSY vacua is at best metastable. For example, and at some point it will always decay, for example, to the BPS state predicted by the weak gravity conjecture. It is important to note that although the weak gravity conjecture motivates the AdS instability conjecture, it is not a requirement. We could have decays that are not the ones predicted by weak gravity. And while all these conjectures have been tested in very different contexts, but there are still some elusive examples, like the DGKT scenario, which works on AdS4 times a 6-dimensional compact manifold with membranes in the smeared approximation. And we want to see to what extent the fact that the weak gravity conjecture doesn't seem to be verified in this case is due to the smeared approximation. And we will go to higher corrections. So what we aim to do, we want to study these kind of systems, membranes working as domain walls between different vacua, and see if they verify the charge greater to tension relation. We will focus on D4 and D8 branes acting as domain walls, and we will go beyond the smearing approximation. And what we find is that the decays mediated by D4 are at best marginal at the order of corrections we are considering. So these systems don't seem to work very well with the weak gravity conjecture, but maybe if we go to higher corrections, this marginality is broken. And then for the D8 behavior, we have more interesting things to study. And we see that beyond the Smithson approximation, the D8 behavior is described by a bionic solution, which we will study later. And the leading correction to the charge to tension relation goes like this integral, relating the, well, that depends on the Kähler form of the Calabi-Yau and also the non-closed part of the world volume flux of the D8. And we see in the examples we study, we see that in all of them, they verify these, that they are a linear combination of the induced tension of D force. And when we apply it to the toroidal orbifold case, in the toroidal orbifold examples, we write it in terms of just topological quantities. Depending on the choice of these charges, of the charges of these explains, we can both build for the toroidal orbifold examples cases in which the charge is greater than the tension and cases with the tension is greater than the charge up to this order of approximation. So let's start with our setup. We will work in AdS, well, in type 2A, in AdS4 times a Calabi-Yau orientifold. And this the kind of vacua that are allowed in these kind of systems was already studied by Joan Kiran and Fernando Marchesano in 2019. And we will focus on two of the many families they found that are built by turning on the NS flux and the G4 Ramon flux, as well as the Roman mass G0. So depending on the value of this factor E epsilon, we can have the SUSY background if the epsilon is equal to -1, or like a sister family of non-supersymmetric vacua when the epsilon is equal to 1. There are many more, but we focus on these two because, well, the supersymmetric solution is the best understood one, and the one with epsilon equals to 1, it's so close to the supersymmetric one that we expect to inherit much of the well behavior. So since we have a non-exact part for the NS flux, we have to introduce also orientifold planes and AdS6 planes to properly build the Bianchi identity for the G2 flux. And we have this relation in terms of, well, the number of D6 planes that we have in our system. And if we want to, in order to work with this in a more systematic way, we introduce a three-form current we call K, defined as the adjoint that satisfies that its adjoint derivative is the two-form flux of the Ramon, and we decompose this in a harmonic basis. So we get to a Laplace equation of this kind, and the harmonic basis we choose verifies that the Poincaré dual of these harmonic basis are the three cycles which are being wrapped by the localized sources of our system, the D6 and the O6, the orientifold planes. So we take some simplifications and we assume that all the D6 planes are wrapping the same three cycles as the one where the orientifolds are defined. So this reduces a lot the variety of cases we have to consider, and also ensures that we can pick the flux volume of the D6 planes to be 0, which further simplifies the problem. And then we can always work with a localized source that combines the charge of the O6 and the D6 as a whole, which we define in this way. Here, for further study, we define the index alpha to label the cohomology class of our basis, and eta the different representatives of the inside of a given cohomology class of these cycles. And in addition, we choose the Poincaré dual of the NS flux to be proportional to the homology class of the orientifold planes. And with that, we arrive to a very simple tadpole constraint between the flux quanta and the number of, and a quantity that is related to the number of D6 planes. It's important to note that this quantity n and both n and h not need to be integers under this in this setup. What needs to be integer is the homology class associated to the product of h times the homology class of the orientifold planes. So we can have like fractional values depending on the on the geometry. So on top of this setup, we introduce the membranes. We will have an AdS4 metric which we write in terms of the Poincare coordinates. Importantly, we use a coordinate set to describe the distance with respect to the boundary. And we put our brains in a very specific position. They are taking, so they spawn the coordinates t, x1, x2. So they are parallel to the boundary at fixed value of set. And we study the relation between the PBI action and the Chern-Simons action. And we see that whenever the tension is greater than the charge, these membranes are driven away from the boundary and collapse. So the vacuum outside of this bubble, it's stable. If the tension is smaller than the charge, then these these bubbles tend to grow, and we have a perturbative instability. And in the case where the charge is equal to the tension, the system is stable at this given position, and the case will be at best marginal. And we have, for example, the BPS systems described by the refined weak gravity conjecture. So we put this into practice and test it for the V4 membranes, both for the SUSY setup and the non-SUSY setup. And we see that both at the Smirian approximation verify the Q equal T relation. So this level, they seem to be in tension with the weak gravity. For the V8 brains, the system is a little bit more complicated because the V8 membranes alone are never BPS, not even under the SUSY background. This is because remember that as we can see in the picture, the V8 membrane acts as a source of the Romance mass. So we have different Romance mass at both sides of the domain wall. And this implies that the number of D6 brains has to change in order to verify the Bianchi identity we saw before. So once we take into account the change in the number of D6 brains at one side of the membrane to the other, there is an induced charge that enters into the BBI, well, into the balance of the system, and makes the full system D8 plus D6 be BPS for SUSY, and surprisingly as well for the non-SUSY case. So and again, when we are working with D8 brains in the Smirian approximation, we can't get away of the relation Q equals tension. So we want to see if all of this is because of the Smirian approximation, and we take into account the back reaction of the membranes over the background geometry. This causes that we lose the SU3 structure, and it's replaced by an SU3, a more general structure than SU3 times SU3. So we no longer have Calabi-Yau manifold. So, and what we do is to expand the geometry in terms of Calabi-Yau manifolds plus corrections in terms of power of the coupling constant. And this analysis has been studied both for SUSY by Jungans and Fernando Marchesano, Rampalti, Joan Kiran, and Alessandro Tomasillo, and also Daniel Jungans, and more recently for this particular non-SUSY vacua in our previous project. So in particular, when we consider this back reaction for the case of the D8, we see that the D8 plus D6 is replaced by a B-ion. What this means is that the membrane develops a non-trivial profile in the internal coordinates. There appears a non-closed volume flux for the membrane that we can write in terms of the free-form current we defined before. And we have to add all the contributions from the different 3 cycles of our basis multiplied by the change. This Q is the change in the charge of D6s from one side of the membrane to the other. And the non-trivial profile, it's given as follows. We have a coupling between the variation in the set coordinate and the variation in the inner coordinates. So for a generic point in the inner manifold, this will correspond to points located around the fixed value of the coordinate set. But as we get closer and closer to the orientifold planes, the set goes to infinity. So we manage to map all the points at one side of the membrane with this mapping. Well, with this new background geometry, we study the D4 brains, and we see that even with the non-Smirian corrections up to this order, we still have Q equals tension. So this we don't manage to go beyond this. But for the D8 brains, the thing is much more interesting, and we have 3 sets of corrections described in this equation. We have curvature corrections as well as a new tension contribution coming from the bion structure. The curvature corrections are two. One comes from the Chern-Simons, the Chern class of the inner manifold, and another coming from the harmonic part of the flux volume of the membrane, and then the one from the bion. We see that depending on the value of epsilon, this can be either 0 when we have the supersymmetric vacua. So even with the bion structure, we still have PPS in the SUSY background. But when we go to the non-SUSY, this quantity can be non-zero since epsilon is equal to 1. And well, some things to take into account is that we can choose the flux, the work volume fluxes to be 0 with an appropriate choosing accordingly the flux quanta. And when we go to a toroidal orbifold limit, we can also neglect the corrections coming from this term associated to the Chern class. So near the toroidal orientifold limit, the behavior is only ruled by the corrections coming from the bion, which are given by this integral. So to summarize the results up to this point, we have this table. So we see that for the d-force, there is nothing we can do up to this point. Maybe if we go to higher orders in the perturbation expansion, we can finally find something that pushes the relation between the tension and the charge far away from the equality. But for now, no. But for the d8s, we have that in the SUSY background, we always have PPS, both in the smeared approximation and bion smearing. But when we go to the bionic configuration, we break this equality. So the next question is, which is the sign of this correction? It's positive, so it supports the weak gravity conjecture. Does it generate instabilities? So Fernando, Joan, and I already tested this in our previous work for a very simple example in a toroidal orbifold over Z2. And in this case, we assumed a very naive distribution of the D6s, so that they were always compensating the charge. They were evenly distributed among all the orientifold cycles, compensating the charge of the orientifold. And there, in this case, we obtained that the charge was greater than the tension, supporting the weak gravity conjecture. The problem is that now that we have looked deeply in these kind of setups, we have seen that this particular distribution cannot be realized as a transition between AdS vacua. So what we're going to do now is study in more detail and with more methodically factorizable toroidal orbifolds to see what we can say about the bionic corrections in this case. So we focus on factorizable toroidal orbifolds of this kind, where we take the orbifold to be like a Zn group or a Zn times Zn group. And in this case, the orientifold planes, we can reintroduce all the machinery we saw before regarding our basis of homologies, like of three cycles, and we expand the orientifold planes in this basis. The good point is that since we are working with a factorizable tori, we can express the 3 cycles as products of 1 cycle, each one wrapping a different 2 tori. And we describe them in terms of the wrapping numbers and nm over the periodic directions of each tori. And then using the harmonic basis, we decompose the bionic correction in terms of the contributions coming from pairs of 3 cycles of our basis. And then we sum them all over, considering the change of charge of the D6 branes located in these cycles from one side of the membrane to the other. And what we found is this formula. Let's describe the rules let's describe piece by piece what this means. We have this sum over the n equals 2 sector of the D branes. This means that we are considering that the only D branes that contribute to the charge to tension relations are those those pairs which have the same wrapping numbers in one cycle, as we can see here, and different in the other two, tori. So they describe planes, 3 cycles that are parallel alongside one of the two tori, and they intersect in the other two. Then the dependence on the cohomology classes of the involved cycles comes in terms of the intersection numbers. Intersection numbers along the 2 tori in which the cycles are not parallel. So at the end, this number is counting the points of minimal distance between the pair of the branes that we are looking. They can either intersect over one cycle, as we can see in this picture, or they can run parallel if there is a certain distance between the parallel cycle, between the cycles in the tori where they share the wrapping numbers. And finally, the dependence. Sorry, can you hear me?
Yes, yes, it's
Yes.
Okay, there was like a, a message from the saying like that the headphones have turned off. Okay, okay. So finally, the dependence between the choice of representative in the homology class of the cycle comes in terms of this factor epsilon. This factor epsilon is either 2 when the one cycles are actually intersecting over the third torus, or it's -1/2 when they run parallel to each other at a certain distance. So this is very important, since we see that depending on the choice of distribution of d-branes we have, we can have either a positive contribution that supports the weak gravity conjecture or a negative contribution that goes against it. So now we try to find examples to see how this works in practice. The first one is again the T6 over Z2 orbifold, which is generated by this group action over the complex coordinates of the torus. And the first thing we need to do is to study the minimal bulk cycles and the flux together with the flux quantization and the topple constraints to see to what extent we can have allowed jumps between d-branes to one side of the membrane to the other. The main challenge here is to identify the true bulk cycles of the orbifold, because what we are giving here, what we are working is with a description in the covering space. So in some situations, the cycles, the minimal cycles in the orbifold are not going to coincide with the ones we are describing in the covering space. So for the case of the Z2, we find these relations. So the Romance mass had to jump in steps of 2, and the factor H we saw before that related the Poincaré dual class of the H flux with the homology class of the orientifold planes is 1/2. And using these relations, we can build several transitions between two sets of vacua. Looking first at the one of the left, the description here is we have each group of three squares represents our 2 tori, our 6 tori, sorry, factorized. The arrows represent the locations of the different orientifold planes. We have all these sets, and on red we put we signal the places where we locate these 6 branes on top of them, canceling the charge of the associated orientifold cycle. So in this case, we have to follow the formula before and sum over all the pairs of these 6 branes that are in the n = 2 sector. So they need to be parallel alongside one of the directions of the torus on one torus. So for example, we have that this direction is parallel to this one. So this will give a contribution to the formula. And since the d-branes are overlapping, the contribution will be positive. And we can take like this one and this one, and this one and this one, and we sum over all of them and get this correction in terms of a sum of tensions of the induced tensions of d4 branes wrapping each of the torus. For this case, for this setup, the relation satisfies the weak gravity conjecture. We are managing to find a system where the charge is greater than the tension thanks to the D8 bion. But if we consider a very similar case, but locating the d-branes in a slightly different manner, so the contributions are the same, but corresponds to d-branes that are not intersecting but are parallel in one of the tori, we get this system. For example, this one and this one, this pair will contribute since they are intersecting in 2 of the tori and are parallel in the third one. But given the formula above, they will contribute with a negatively to the charge to tension relations. And all the contributions in this case are negative, and we get a a correction to the charge to tension relations that makes the tension greater than the charge. So this example is in tension with the weak gravity conjecture. We move on and consider other kinds of toroidal orbifolds. We mainly focus on Z4 and Z3. The distribution of the orientifold planes changes, as we can see in these pictures. We start describing the different orientifold planes along each two torus that is factorized. But for example, for the Z4, we are able to recover again examples that are in tension with the weak gravity conjecture in a similar way to the Z2. We briefly overview the cases of the Z6 and Z4 times Z2 example case orbifolds. And we also see that in all the examples we can find, they verify this formula. So to wrap up, we have seen that we have tried to determine whether the Q is greater than the tension for systems in non-SUSY vacua, consisting of families of D8 plus D6 planes closely related to supersymmetric solutions. And at leading order, we see that the Q is equal to the tension, but at high orders, we have to introduce the bionic description for the system, and we have two unavoidable corrections. One that goes with the Chern class of the compact manifold, another one that goes with the bionic correction. And this last one always can depend, the sign with which it contributes can depend on the distribution of these explains on our system. So when we go to the orbifold limit, the bionic correction dominates, and we can build cases with the tension greater than the charge. These cases correspond to situations in which we have pairs of these explains that do not intersect. So there is a finite distance between them in which open strings can spawn. So we will have like massive states that are above the compactification scale of our system. This is in tension with the weak gravity conjecture, but note that it's not in tension a priori with the AdS instability conjecture, since we could find other decay channels like D4 bubble nucleation. And some possible caveats is that we will need to take into account one loop corrections, since these corrections will depend also on the position of the D6 planes and could push the energy of the system in such a way that these transitions are no longer favorable for the T greater than Q. At a face value, our results suggest that the N equals 0 AdS4 vacua with each sector without zero light modes, it's more stable than the ones in which it contains charged light modes due to the overlapping of the D6 planes. Well, in any case, even if the one loop corrections are the solution, then this computation can also help us to understand how to compute this kind of one loop corrections in non-SUSY cases. And if that's not the case, maybe we have to think about how we phrase the weak gravity conjecture in these kind of membrane systems, because they are pretty weird in the sense that, for example, they don't satisfy the thin wall approximation, and their charges are bounded by the Talpo constraint. So when we look, for example, at the convex Hall condition, which is one of the ways to formulate the weak gravity conjecture, this one is formulated taking into account that the charges are not bounded. So all of these can help us maybe to better understand the weak gravity conjecture and its relation with the membranes. And with that, I finish. Thank you for your attention.
Okay, thank you very much, David, for the nice talk. Are there questions from the audience? Let's see. Otherwise, I have several. Okay, let me start asking while people decide. So first I was wondering, when you say charge equals to tension, in the weak gravity, there is always some order one factor there that you fix with extremality or with the repulsive force condition. You know, I mean, how are you fixing these numbers? You are thinking just of breaking the BPS condition, like more like the repulsive force condition, or you know that is also equivalent to the extremality and it's about the weak gravity conjecture?
I think we are only thinking in the BPS condition. We are not focusing on those factors really. I'm not sure.
Because then it's not necessarily a violation of the weak gravity, but more of the repulsive force condition. But it could be that that they are equivalent in this case. I don't know. One should check.
Okay. Yeah, I'm not sure about it.
More questions?
Yeah, I have a question. Is there? Do you think you could engineer a setup, because there's the one loop corrections that could change the result? Have you quantified that? Are there any corners in parameter space where you could actually, argue that the loop corrections are very small, or they have to be smaller than the shifts that you found?
I don't really know. We haven't thought this. We would like to think about it, but we haven't taken into account at all. It's still the one loop corrections. The only thing we saw is that they do depend on the position of the D6 frame. So
I see.
Maybe, but we didn't go far beyond that.
So sorry, you explained this, but is there like a large flux that you make large in this setup? The number of D6 frames or
no, the number of D6 frames. No. In fact, the number of D6
there's
frames
no number
very...
you can make large, right? Like
no.
So you're given a Calabi-Yau, you can put this many, and you're given another one this many. I see. I see.
Yes, for example, for the case of the Z2 Z2, we can put at most like 32.
Right.
This is because it's about the D6 and not the D4, right? Like the F4 flux then could be large.
Yes.
And I was wondering also about the loop correction. So you cannot estimate if they should be more important or less important, and then once you compute it, and there's no way to know this.
I don't know, but what we thought is that if we believe that the weak gravity conjecture should hold in these kind of setups, that could already give us like an order of magnitude for the one loop corrections. So it was a little sort of backwards the reasoning we did in that regard.
And can I also ask, like in the DGKT example, which is considering this orbifold, right? Does it matter the distribution of the branes? I mean, you get scale separation also for the cases satisfying or violating the weak gravity conjecture?
I will say so, but I'm not sure. I think they don't look so in such a in so much detail a particular location of the D6 frames. But yeah, I think that will be an interesting thing to check. Yes.
Okay. So I think there are no further questions. So in that case, thank you so much, David, for the nice talk.
Thank you.
It's very interesting. So let's thank the speaker again. And hope to see everyone next week.